This is an implementation of a 1-bit memory using NAND gates. The implementation uses 5 NAND gates for the D flip-flop and 4 NAND gates for the MUX. So the NAND gates are combinatorial logic, and with the clock they form sequential logic and this 1-bit memory. Here's the clock. It's single state, push button at the moment. On, off, on, off. I have an input 1, 0, 1, 0, and I have a load enabled, load disabled. So to get a 1 from the input to appear and be stored in the memory, I need to put a 1 at the input, enable the load, and then single step the clock. And on doing that, we see that a 1 is stored in memory and appears on this output LED. Regardless of what happens to the clock, that 1 stays there. Regardless of what happens to the input, that 1 will stay there, stored in memory. To store a 0, I currently have a 0 at the input, so I will load, or I will enable the load and then step the clock, and we see that the 1-bit of memory now has a 0 in its memory register, 1-bit memory register, regardless of what happens to the clock, and regardless of what happens to further input changes, that 0 bit stays there. Now this clock also has a free running mode. So let's do the demonstration again. Let's put a 1 at the input, and when I enable the load on the next clock cycle, we'll see a 1 at the output. And there it is, and that 1 stays there regardless of the status of the clock and regardless of what the value of the input is. And to get the 0 stored in that 1-bit memory, I will enable the load, and on the next clock cycle the 0 will appear. So now we have a 0 at the output, so a 0 in memory, regardless of what's happening to the clock and regardless of the status of the input. And that concludes the demo of a NAND gate implementation of 1-bit memory.